lipid. So let us continue our discussion from what we were discussing yesterday. So we have discussed to some reasonable detail how a system call works. That in earlier days, system calls used to be handled like interrupts, but modern architectures have developed some more efficient mechanisms, such as having a set of registers to store the system call handler routines. I mean the address of the system call handler routines, etc. However, towards the end of yesterday's class, we also discussed that when we write programs in a high-level language like C, we do not have to worry about all these details like a syscall instruction, whether it will access some registers or the IVT or something like that. So the operating system is hiding all those details from us. So when we do, till now, when you are writing programs in C, you are using printf and scanf. In this course, so this printf and scanf used to be translated by the standard C library into calls like read and write. So for all practical purposes, these are called system calls, things like read, write, etc. Okay. Underlying the kernel actually calls this syscall instruction, but we don't need to go into that level of detail in order to write our programs. So till now you are using printf and scanf, right, in your C programs. In this course, and maybe also in the networks course, which many of you are doing, you would actually be asked to use some of these APIs, some of these system calls. And now we will call these as system calls only. Okay, my voice is not clear. Maybe because, there are some network issues in my programs, I don't know. Anyway, I really cannot do much about this, maybe apart from speaking a bit louder. But the IT Kharagpur network has been undergoing some issues since yesterday. Anyway, try to bear with it. Yeah, so basically in this course, when we say about system calls or when we discuss system calls, we will be at this level. We will use calls like read, write, etc. Right, so this was an example which we gave yesterday for read. So as you see, this is again very similar to a function call from your perspective, from the programmer's perspective. And that is because the operating system is giving this API to make system calls easier. Okay. So like this read system call takes as arguments a file descriptor from where the read will happen, this memory pointer where the data that is read will be stored, and the size which says, the count which says how many bytes to read. And so count number of bytes will be read from this file descriptor empty and stored in this memory location pointed to by buf. Right? So this is a simple API which the operating system is giving us to do the read system call. The underlying details we do not need to know, though we have discussed a bit yesterday. Okay, if there is some disturbance in my voice, I can leave and join once more, but I don't know if that will. Okay, let me leave and join once more. So let the meeting stay, but let me leave and join once more. Okay, hello everyone. Am I audible? Okay, so let me again start sharing, etc. Is my screen visible? Okay. Fine. So, yeah, as I said, as I wrote, there may be some problems with the network, but I really cannot do much right now. I will try to speak slowly. So yeah, we saw this example of a read system call, right? But this is just one system call. There are actually like several hundred system calls, right? So I think there are close to 300 system calls in Linux. So now we will see about some of the other system calls very briefly. So we will just discuss some of the names of some system calls, but we will not go into details about how they work. But I would suggest, I would point out resources where you can go to know more details about the system calls. Okay, is what I am saying understandable? Or is the situation so bad that you cannot even understand? Okay, thank you. So let us proceed and see some system calls. So there are different system calls for different purposes. So there are some system calls which are for process control. Now what is a process? Typically we have been using different terms like job, application, user program, etc. From today onwards we will see that we will specifically use this term called process. Okay? So a process is basically an application. A user application you think which runs. So there are different system calls for process control. As in, like you create a process. So one process is running and it wants to create another process. Similarly, one process wants to terminate another process. One process wants to wait for time. It waits for a process wants to wait for some event. The process wants to allocate on free memory. Till now, we have been doing this with malloc or calloc. But understand that somewhere the process needs to request the kernel to allocate some more memory. So there should be system calls for allocating and freeing memory. Then there is something called debugger. Have any of you used a debugger like the GDB debugger, GDB? Any of you use that? Okay, good. So, do you think that debugging would require system calls? Why should debugging require kernel support? What do you think? So you can unmute yourself, one of you, like Dhunil, Ayut, Mukul. Yeah, exactly. Okay. So what Shubham and Mukul have written, that is the idea. Maybe for those who have not used a debugger, this might not make sense. But in general, so the situation is like this. You have written a program and maybe you are getting segmentation fault. You do not understand where the fault is occurring. Or even worse, a logical error. That means your program is working perfectly, no segmentation fault, nothing. But at the end, the answer is not coming out correct. The actual output is wrong. So then what to do? How to understand? So what to do when a program does not work? Changes as you become seniors, hopefully. So in previous lab, if your program does not work, you immediately stand up and call other people to help you, like TAs or the IT member. That is okay for the PTS lab, but maybe when you have become a bit more senior, even then you can run to your next room and ask for help. But a better way is to debug your program yourself. And for that, a tool called debugger is often used. So using a debugger, you can say things like, after every statement is executed, you want to check a particular variable. Right? So you want to check a particular variable in your program after every instruction is executed. So now think about it. Your program does not have a print statement after every instruction. So your program cannot show the value of the variable after every instruction. Some other program will show it, that is the debugger. But then the mechanism will have to be that after your program executes every step, it should be stopped. The debugger should be run, and then the debugger will show you the value for that variable. This should be done after every instruction your program executes. So then you understand there is a need for frequent switching. So your program is allocated the CPU, it executes one instruction. There should be some mechanism to say now your program will not run any further. Rather, control will come to the debugger, or the debugger should be allocated the CPU, so that the debugger can show you the value of that variable. Right, so all these things require kernel support, and therefore they require system calls. I am not going to explain, so this class is not meant for explaining debuggers, but those are very useful tools. If you have never used a debugger, I would strongly suggest you look up a debugger and try to familiarize yourself with it. They are very useful when you have to debug your own program. Okay, let's move on. So the previous slide showed some examples of system calls for process control. Now there are more system calls for file management, like opening a file, closing a file, reading and writing, getting and setting file attributes, and so on. So these are what internally printf, scanf, getters use. Okay. So in a C program we write printf, scanf, getters, and getters. Internally they use these system calls: open, close, read, write. Then just like file management, there are system calls for device management. Like requesting for a device, releasing a device, reading or writing from a device, etc. Okay. I'm just telling you the names of some system calls, but and in the last slide of this deck, there are several research cells which you can check to get the details. Also, the next lab assignment will require you to familiarize yourself with a lot of these system calls. Okay. Similarly, there are times when one process needs to talk to another. Okay. So this is called inter-process communication, or IPC in short. One process needs to talk to another. So here, just to draw one analogy, okay, let me ask, can you think of any situation where one process needs to talk to another? Talk means share some data, etc. Can you think of a practical situation where this can happen? File reading. Why? Why should one process need to talk to another? Please elaborate a bit. Okay, Mukul has given a very good example. Okay, Devachati, I am not understanding your example. A file needs to be opened. Sure, you all have written programs which open a file. So why should one process, a program or a process opening a file, so why should this require inter-process communication? So Devachati, can you unmute yourself?
Yes, sir. Hello, I'm audible.
Yes, go on.
Yes, sir. I wanted to mean like you are running a Python script to check a C program output. So you need to run the C program, take the output, and then check in Python. I'm giving that.
You want to write a Python program to check the output of a C program. Devachati, that is what you are telling.
Yeah. Yeah. Basically, I'm checking the C program output with the Python program.
Has it already run and generated its output in a file?
Sorry.
Is the C program and the Python program, they are running at the same time? Or has the C program run earlier and saved its output to a file?
No, the Python program will internally execute the C program.
Okay. Yes, then it is possible. Yeah, that inter-process communication is required. Fine, okay, you can mute yourself. Okay, so yeah, so basically when or the example which Mukul gave, so often we say that you want to send the output of one program to another. Okay. So let me just demonstrate one small thing. Can you see a shell on my screen? Can you see a shell? A command line. Okay. Suppose I want to do a very simple task. So if I do an ls, it will tell me how many folders, etc., folders or files are there in this current folder. I want to count how many files are there. Of course, here there are only few files or folders I can count by hand. But suppose you have a folder having thousands of files. I want to count how many files are there. What is a good way of doing it? Like you can possibly write a program, but do you need to? Or are there standard facilities given by Linux, which will tell you, which will give you an easy way of finding how many files are there. Exactly, good. Mukul and Sean have said ls, something like this or symbol, wc minus l says 12. Okay. First of all, what is ls? Everyone knows. What is wc? WC is another inbuilt program, just like ls. WC stands for word count. Yeah. And what is WC minus L? Line count. Yes. WC by default will give all, like if you just do a WC, it will give you character count, word count, line count, etc. I specifically want to count number of lines, therefore WC minus L. But interesting thing is here, ls is one, let's say, program. I want to send the output of ls into the other program, which is WC. Right? So I am using two programs here, ls and WC. And I want the output of ls to go to input of WC. How to do that? By this. This is called a pipe. A pipe, okay? So, again, in the next assignment, you will see these things. So, this is an example of inter-process communication. Output of one file goes to input of another. And output of one file goes to input of another. Okay. So, there can be many other situations, like you have a huge table on which to do some operations. Now, if you run only one thread or one process, it will be able to do everything, but it will take a lot of time. Therefore, you want to make things parallel, run in parallel. So you want to run 10 different processes which will concurrently work on that array or on that matrix. But then they need to coordinate among themselves that which part of the array one process is working, which part of the array another process is working, and so on. So this kind of coordination between processes need inter-process communication. Okay. So there are many different situations where one process needs to talk to another. So the operating system gives, or a kernel gives, several system calls for such inter-process communication. Okay. Also, there are several other system calls, like say for protection. So you would like to specifically, so I think you know that, at least, even if you don't know, you can guess. Protection is a very important concept in systems, because you cannot allow everyone to access every file. So there are some files which only a particular user can access. Like there are some files in your home folder which only you can access. There are some files which you are okay with sharing with someone else. Right? So maybe your lab assignment programs, ideally only you should access that. But someday you may want to share it with some friend of yours. Right? So for all these things, system calls are there. Though, again, a disclaimer, sharing assignments with others is not a good way of trying out system calls. Right, so keep your assignments to yourself. And yeah, for all these things, like to control which file you will only be able to access, or which file others will also be able to access. Or maybe you are okay with others reading a file, but you are not okay with them changing the file. That means you would only like to give them read permission, but not write permission. Right, so all these things require kernel support. Right, so for these there are system calls. Let's say chmod, chown. So chown is change ownership. So you would like to make someone an owner of a file. Right, so that is change ownership of a file. Usually I don't know if you have observed these things, but I mean, every file has an owner, right? Every file has an owner. So again, if I just can open up this shell, if I do an ls minus l, okay, this gives lot of details about the files. Can you see this? Can you see? Can you see what is written in? Is it readable? What is written in this shell?
Yes, sir. Yes, sir.
So see, there are some things like sghosh. Okay, first of all, this is the file name. These are the file or directory names. Okay. There is this sghosh. This is my login name, but basically this is telling you who is the owner of the file. And you see these. Any idea what these are? RWX, what are those? Exactly. These are permissions, file permissions. R is read, W is write, X is execute. Okay. So these define which file has what kind of permissions. Also, if you look carefully, there are three groups. See, one RWX, second another RWX, and third another RWX. That is because Linux understands three types of users. One is you yourself. Second is there is a concept of user group. So some trusted users you have put in your group. So that's a group. And the rest of the users are others. Right, so user, group, others. So the first three are permissions for yourself, user. The second three are permission for your group. And the third set is permission for other users. Okay. So see this one which I am highlighting. This says that you have the permission of read, write and execute. People in your group have the permission to read and execute but not write. So they are not allowed to change anything. Similarly, others also have the permission to read and execute but not write anything. So that dash in place of W says that the write permission is not there. If the write permission would be given, then it would be RWX. So suppose you have a file where everyone has every permission, then it would be RWX. Okay, one clarification. We are not using any system calls right now. We are just like, okay, not sure. Ls maybe using a system call. I have forgotten. Anyway, but I am saying that I have not demonstrated use of any system call right now. I am just demonstrating to you the output of ls. But ls internally may have used a system call to get the folders or to get the contents of this folder. Okay. But okay, if you think these are very difficult, not actually so, because the assignment that is the next thing, the very next assignment in the OS lab will ask you to actually do these things. They are not so difficult if you know. So, okay, I have given a very brief overview that there are different kinds of system calls. But if you want to know details, there are several resources. Just one simple Google search will give you a lot of information about system calls. Right? So, nowadays information is quite free. Okay, so that ends our discussion on system calls. So, any questions before I pass on to the next topic? Okay, if not, let's just start the next topic, which is called processes. Okay. me just start with this background that till now we have been using several different terms to mean kind of the same concept. Task, user program, application, etc. etc. From now on, as I said, we will specifically use this term process. So this lecture will tell you what a process is, how is it stored in the system, and so on. So what is a process? A process is a program in execution. Understand clearly that we are differentiating between these two terms, process and program. I'll come to it. So a process is a program in execution. So if you recall multitasking, we said things like, now we will specifically use the term process, that several processes are there in the computer system memory, and at one point of time, the CPU will be allocated to only one of these processes. But there is frequent switching. That means at a particular time t, maybe process P1 is running. At time t plus 5, maybe process P2 is running. At time t plus 10, process P5 is running, and so on. Right? So several processes are there in the system and system memory, and they are running concurrently. We don't say simultaneously, but we say concurrently, because at one point of time only one process is running. But this is happening so fast that every process is getting an illusion, or at least the users, we are getting an illusion that all the processes are running simultaneously. But actually it's not simultaneous, it's concurrent. Right? Okay. So yes, so CPU switches rapidly between several processes, and we say that the processes are executing concurrently. But this happens so fast that users get an illusion that their program is always running, or their process is always running. But that's not the case. So as I said, we will clearly distinguish between these two terms, process and program. A program is a passive entity. Like you write a C program, a .c file, that's a passive entity, as in that's just a file. A process is an active entity, which is actually running on the system. So a program becomes a process when the code is loaded in the memory and is ready to execute. Okay. So a program becomes a process when the code is loaded in the memory and is ready to execute. So let me ask, suppose you have written a program, hello.c, it's a program. When exactly will it become a process? Okay, Shamnath, when we execute the object file, but can you make it more specific? Like, what do you mean? When we give a particular command? Exactly, when we give the command error out. Again, see, compilation does not make our program a process. The compiler runs, it reads our program file, it compiles it, produces the other code, etc. etc. Our program, hello.c, becomes a process exactly when we give this /error out. Then some other program, possibly called a loader, will load our program into the computer memory as a process. So then it becomes an active entity. Okay? So clearly differentiate between program and process. Also understand that each execution instance of the same program is a separate process. Suppose you have this one program hello.c. You run it once, then it became one process. Suppose execution is over, you again run it. It will be a separate process. So the program again remains the same, it's still hello.c. But every time you are running the program, a separate process is being created. Okay. Another small question, is it possible that multiple processes of the same program from the same program are being concurrently executed? Is it possible that multiple processes that all running the same program are currently in the memory and all are executing? Okay, it is very much possible. Yeah, it is very much possible. So Mukul, I'm not asking about multiple threads of execution. I'm saying the same program running as different processes. Now again, process and threads are not exactly the same. Now we are discussing about processes. In a later lecture, maybe 3 or 4 weeks later, we will discuss threads also. So processes and threads are not exactly the same. So I'm not discussing about threads here. But yes, it is very much possible that multiple processes coming from the same program are running. Just think about it. When all of you are doing a lab, say in a computer server, when you used to be at IIT Kharagpur campus, there's a programming lab going on, algorithms lab going on. All of you have logged into the departmental server, and you all are using a particular program, say BI, to write your programs. Or you are using gedit. Now think about it. Gedit is a program. But then 60 or 70 of you are simultaneously using gedit to write your own programs. So many processes are running, right? But all of them are using the code of that one program gedit. Okay. So it is a very common situation that many processes are running and all of them are using the code of the same program. So gedit. Okay. So again, understand clearly the distinction between program and process. A program is just a static entity which sits in the disk, a file. A process is an active entity, and several different processes can run the code of the same program. Okay. So I hope the distinction is clear. If not, please feel free to ask. Okay. So now, just 2 more points before starting to discuss about processes. Sometimes you will hear of the term job scheduling and sometimes you will hear of the term process scheduling. Well, in this course, we will focus very much on process scheduling, but we will also hear this term job scheduling sometimes. This distinction comes from a bit of a historical perspective. So in earlier batch processing systems or multi-programming systems, we have discussed this, remember? Initial programs were called jobs, right? And there was this concept of loading a job into memory. That was usually done by a long-term scheduler. There were 2 types of schedulers, a long-term scheduler or even today there may be some equivalent programs. So long-term scheduler loaded jobs into memory. Whereas a short-term scheduler actually allocated the CPU to the jobs. Let me explain by this picture. So say that there is this lot of jobs are waiting in a job queue. The long-term scheduler will pick one of these jobs and will put them in the memory. Right? Yeah. And so now different jobs are waiting in the memory itself. The short-term scheduler will actually choose one of these processes in the memory and allocate the CPU to it. Right? So again, job and process, we will not use the term job for much in this course. But yeah, from a historical perspective, there was this distinction about job queue and process queue. So a long-term scheduler loaded a job into memory, and a short-term scheduler chose one of these processes. So once the jobs are loaded into memory, they become processes. Right, so there is 2 levels of scheduling. One is there are many waiting jobs, so which job to load into memory. That was decided by the long-term scheduler. And once someone said there are say 10 there are say 100 jobs waiting, and 20 jobs are in the memory, they are currently processes. So the short-term scheduler selected one of these 20 processes and allocated the CPU. But okay, this is mainly from a historical perspective. We won't discuss about job scheduling much. We will specifically discuss about processes and process scheduling. So let's discuss, now that we have understood the difference between process and programs, now let us talk more about processes. So let us start talking about the structure of a process. So what we are specifically discussing is, as I said, a process resides in memory. How does it live in the memory? What are its contents? So a process has the text, that means the program code. As I said, every process is executing some program code. So it has one portion of the memory dedicated to containing the program code, which is called text. This segment is called text. So, this segment is called text. Then it has another segment called data, which are mainly used to store global variables. Think of your C program also. When your C program is actually running, this is how it looks in the memory. There is this text portion which contains the program code. There is this data portion which contains the global variables. There is a portion called heap, which is initially allocated, but this is the portion which will be used if you dynamically allocate memory. So this is called loop. Then there is another portion called stack, which is meant for storage of temporary data, function parameters, etc. So I think from your compiler knowledge, etc., you know that when you call a function, something is pushed onto the stack. Okay? So the arguments of that function, etc., they are possibly pushed onto the stack. So the stack is for those temporary data requirements, local variables, router addresses, etc. Right? And in between there is empty space or unallocated space, you might say. So the idea is that the stack goes top downwards and the heap goes bottom upwards. Okay. So these things new, or you are kind of familiar with these from compilers, etc. Fine, so I hope that you have understood that this is how a process looks like in memory. I thought this would be known, but anyway. So there is a portion which contains the program code, the text, a portion which contains global variables, and then these two which are initially unallocated, but they will be used during execution to store dynamically allocated memory or temporary data, etc., the stack and so on. Okay. Also, if you think the process includes all these, the program counter, the simply registers, open files, etc. So maybe your program has opened a few files, or you will be writing. So someone must remember those things, right? So usually these things are also parts of a process. Okay. Any questions? Okay, so what is Subhash asking? Is it necessary that the entirety of the program is in main memory for it to be called a process? I'm not very sure about the question. Are you talking about this part, the program code? Whether the whole program code needs to be in memory? So maybe Sriyas, just unmute yourself.
Hello, sir. Am I audible?
Yes.
Yeah, sir. I was referring to the entire part, sir, including the stack heap and everything. Usually, they're a part of main memory. Does it have to be completely in main memory, or can like some variables still be on the secondary memory, like in a disk, and still be classified as a process?
Ask this question about main memory and cache, then I would be a bit unsure, but definitely it has to be in the main memory. Though I must say that there are several abstractions going on, so yeah, I mean things get complicated at some point, as in, okay, I can say this, logically it should be in the main memory, right? But you may have noticed that a part of the disk can also be logically used as memory, because sometimes we are talking about subspace, etc., etc. Also, there is the concept of virtual memory, which we will talk about later. So, yeah, I mean, physically, part of the disk may also be used as memory. But yeah, again, logically, the whole program should be in the main memory. Logically, the whole program should be in the main memory. Yes, of course, which every process has its own dedicated stack. Of course, every process has its own dedicated stack, including the kernel. Remember, the kernel has its own stack also, which it uses to remember about processes which are deallocated from the CPU, etc., etc. I mean, so every process has its own stack. Okay, so that is how a process looks like in memory, abstractly. Right, it has its own text, set data, heap, stack, etc. And as I said, several different processes can actually use the code of the same program. So you see, it is possible that this text portion is the same for many processes. For many processes are many instances of say the GADIC program is running, or many users are using the browser. So this text portion will be the same for all of them possibly. The other portions would be different because every program, I mean every instance is having its own data, etc. But the text portion can be the same for many processes. As if it can be, I mean I'm not saying it's shared or something, but what I'm saying is the contents may be the same for many processes in this text portion if they are running the same program. Okay, now just let me give you a peek into what we are going to discuss tomorrow. So now a process can be set up many different states. Okay? A process has different states. And at a particular point of time, a process may be in one of several states. And the processes change state based on certain events. So this might seem familiar to you, like what you have discussed, what you have read in an automata course. Right, so you know about formal automata and those kind of things. It's something somewhat similar. A process has different states, and at a certain point of time, a particular process is in one state. And processes change states based on different events. So we will discuss about these process states and what makes a process change from one state to another tomorrow. Fine, so I'll end today's class. If you have any questions, please ask. Okay, if not, let's end this class. We will continue tomorrow.